Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We have today visiting Vinay. He's a PhD student at the University College London, at the University College London, right? Yeah. With Ingemar Cox, his advisor. And Vinay will be presenting on some of the work that has been done as part of his PhD thesis. Microsoft has been involved as a sponsor for PhD Statistic, but also active collaboration between himself and his advisor at Microsoft Research in Cambridge. So today he will be presenting on two themes in his work. One is use of relevance feedback, and the second part will be on estimating the effect of user searches. The second part was subject of the presentation given at CBIR, yesterday, I think. So for you who were present at the CBIR, there will be some repetition, but the first part is presented in this. Please.
And thanks. That saves me the trouble of reading the title page out to you. Essentially, as Natasha just pointed out, I'm going to be talking about two themes that possibly don't have much in common apart from both being part of my PhD. But I'll try to string some sort of relationship between them. In the first bit, I'll talk about an evaluation methodology that we propose that we use to compare relevance feedback algorithms. Because traditionally, that's a hard problem. If you don't know what relevance feedback is, I'll just explain it to you in a minute. Then after proposing the methodology, I've just given you an example of how we used it, and to try and make it relevant to Microsoft, it is web search. The second is query performance prediction. Again, it's probably quite unclear outside of the academic community exactly what that is. But it is a very practical problem, and I'll just go into detail as and when we get there. So I mentioned that the first part of the talk is going to be an evaluation methodology for comparing relevance feedback algorithms. We call it, exploring the entire user space, and trying to be quite cute in making the pun about relevance to feedback. Right. So that tells you why we did what we did. So we all use web search engines these days, and it's becoming harder and harder to come up with ranking functions that are going to be applicable across the board. And one way how search engines could keep up with user expectations is to try and make a search interactive process. So what that means is instead of just the user typing in a query and then sitting back, they continuously interact with the search engine, repeatedly providing it with more information and better the retrieval. Relevance feedback is one mechanism that allows this interaction. What it essentially is that you punch in a query and you get a set of results. You look at the results and you pick some subset of them that you like and tell the search engine that either this particular set is relevant or it's not. The search engine now uses this extra information possibly to reformulate a query by adding extra terms, by changing the relative importance of the terms, and then it goes away and gets you a new set of results which hopefully addresses your information needs slightly better. The problem essentially is that there's some sort of unsaid beliefs in the academic community regarding relevance feedback. Or people won't use it, so why implement it in search engines? We won't have multiple feedback because it doesn't work. Also is the problem that just as designing a retrieval function is difficult, designing a relevance feedback algorithm is difficult because you can't design an algorithm that works for all users in all contexts across all queries today, tomorrow, day after, and ever after. So these sort of things make it difficult to even compare or evaluate the performance of any given algorithm because it's very difficult to define exactly what the success of a feedback algorithm means. And this has led to almost no representation of relevance feedback in commercially available search engines. I think the first one or two that came out did have an option but was quickly removed. My personal opinion is that this is because we have not been able to show almost conclusively that feedback is going to help. You're asking users to perform an extra bit of work, so you should go through the effort of trying to convince them that this extra effort that they're putting in is going to come with some benefits. And if these benefits are shown clearly, then presumably they'll be willing to do this extra work. So evaluation in search is quite difficult, as you might know, because given a set of queries, it's so difficult to mention or to clearly identify which document is going to address that query. And even if you did have those sort of judgments, then it's difficult to compare different ranking functions or different retrieval systems just because they might be working on different data sets and things of this sort. At least in the academic community, we have what's called the Text Retrieval Conference, which puts out these standard data sets that everyone working in the field uses. This is the collection that's being searched on. They also release a set of queries that are a substitute to real-world user queries. And they have hired people who sit down and map these queries to documents within the collection so that any person who wants to have any kind of research in the field uses the standard gold data set, and they can easily calculate how well they did in terms of identifying as many as possible of those retrieved relevant documents in the data set. So this is like one-shot retrieval. You put in a query, you get a set of results, and you can always evaluate it versus the data set, labeled data set that you have. But the problem still exists for interactive information retrieval, essentially because there are a lot of aspects of evaluating interactive retrieval that are very subjective. Users might like a retrieval not because it's giving you more relevant results, but because maybe they like the layout on the page that they're using to interact with the system. And to get around these aspects, the way people usually evaluate interactive systems is to conduct user trials. And as you can imagine, it's very difficult to conduct user trials of large size. It's expensive, it's time consuming, and even if you do collect a bunch of people willing to go through your user trial, the size of this group is likely to be quite small, and therefore it's very difficult to make extremely generalized statements about how future users are going to behave, because you've just tested it on a very small set of people. So this is our proposed solution, especially for comparing feedback algorithms. What we're saying is that if you have a very simple feedback model, in the sense that the sort of information you're expecting from the user is very simple. You don't give them too much choice. They only have an option of one or two different things that they can do. Then you can imagine that algorithmically you can simulate a situation where you can measure every possible effect of every possible user action. This is sort of a brute force strategy, but it helps you get an understanding of how any change in user behavior is going to reflect in terms of effectiveness of the retrieval process after modification by the feedback process. Another advantage is the fact that since you're expanding out every possible user action, you can identify this one user action which gave you the biggest benefit. And this sort of provides you with a sort of upper bound on the performance of your algorithm. And this sort of upper bound would be most helpful, at least it gives you a best case scenario. In the context of search, this is quite logical that there are different types of behavior that you would observe when people are using search engines. The first is you yourself would have seen situations where you knew exactly what you're searching for, and once you found that one single document, whether it's the web or a single or a local collection, all you need to do was find that single document, and then you are happy. Whether this document was something you'd seen before or whether it just so happened that it contained all the information you were looking for. It was one single document. This could be something like you've read a paper before and you're trying to find it again, or something of that sort. The second is a sort of more subjective, wider search, where you're looking for things of a certain theme. You might be searching for pictures of Seattle, for example, and there's a sort of topicality involved in this. And again, it's subjective, because what you label as a photograph from Seattle may or may not be labeled as the same by someone outside. Then there's a third class of information seeking, which is just open-ended browsing. They may or may not be looking for anything in particular, and even if they are, they probably have an extremely vague idea of what they're looking for. And it's also possible that while they're looking, their ideas change. Of these three, in terms of evaluation, you can imagine that the first one is the easiest, because it's really clear and there's no argument. When you find the document, you're done. So in that sense, from an evaluation perspective, it's extremely easy. We'll stick to target document search exactly for that reason. With respect to feedback algorithms, feedback as a technique has existed for about 35 years, and you can imagine there's a whole array of feedback algorithms that you can choose from. We picked three in particular. The first two are sort of standard in information retrieval literature, and the third one is a slightly new one, which I'll explain. I'll explain all three anyway. Right, so Rcio was an algorithm developed in the late 60s, and it is probably the simplest amongst a lot. There's the standard vector space model in information retrieval, where every document is represented as an array of term weights. Here I have document DI, where term DIT, for example, gives you the weight of term T in document I. So this weight characterizes the importance of this term to this document. So if this term helps in characterizing this document very well, then this weight is going to be high. The simplest way of calculating this weight is what's called the TF-IDF model, where you take a multiplication of two different factors, one local and one global. Essentially, the assumption is that if a term occurs multiple times in a given document, then it's going to be important to describe this document. And secondly, if the term is extremely rare across the collection, then again, its importance is high. So when you multiply the two, it gives you the weight of the term in this document. So the document vector is then normalized for length, so they all become unit vectors. When you're given a query, it's also pseudo-document in this same space. And to measure the similarity between the query and the document, you just take the cosine dot product. So that was just plain vector space retrieval. What does Rcio algorithm ask you to do? Well, as I mentioned, feedback expects the user to give you a set of judgments. These documents are relevant and these are not. And once these judgments are given to you in these sets, capital R and capital N, the weight in the query is modified by the equation given below. It's just a linear sort of perceptron kind of update in the weight for the term in the query. The second algorithm is what's called the Robertson Spark Jones algorithm, and it comes along with the probabilistic model of information retrieval. Again, it's probably not useful to go into too much detail, but this algorithm differs from the previous one in one specific way. This algorithm also considers what's called query expansion. Your initial query was bad because it was probably not specific enough. So it kind of helps to use the new relevant information provided to you by the user to find additional terms which are likely to be useful. For example, you could go to a university website and just type in computer science. It's going to be so general that you're going to get a whole list of pages, whereas what you're looking for is probably just computer science examination forms. So these extra terms, examination and forms, might have to be appended to the query. You might not know which are these best words to add, and therefore you provide judgments, and then the algorithm automatically finds these terms and adds them to the query. And how it finds these terms, it's there in the maths, but it's fairly standard, this algorithm, and it was designed in the early 70s, and it's probably one step ahead of Rcio in terms of complexity. The third algorithm we are talking about is a Bayesian algorithm. It was designed for content-based image retrieval, but we decided to see how it would work for text. This differs from the previous ones in the sense that since it was designed for images, there is no query. We don't see any queue anywhere on the screen. How it works is that it associates every item in the collection with a probability that it is what the user is searching for. And every time you provide any kind of relevance information in the set capital R, you update this probability in some way. How you do that is given in the equation. All the updates are dependent on some definition of similarity between documents. And in this case, we're using the TF-IDF representation and the cosine dot product for this similarity. So just to bring in what we exactly did in our experiments, we wanted to see how each of these three algorithms would work in web search. We don't find too many web search engines using relevance feedback. We're trying to measure if it would serve them any purpose if they did. As we all know, we have typically 10 results per page in web search, and we know that users don't go beyond the first couple of screens, maybe not even beyond the first screen. And we also know that there is more information on the web apart from just the text that you see on each of these web pages. So we'd like to use any of this evidence to try and improve our feedback algorithms. So this is how we perform our evaluation. Consider a query that's been submitted to the search engine, and you've got a long list of results. 1 to 10 is what you'd see in your first page. And this is the set of results that the user has before him or her on which they're going to pass judgments. They're going to label some subset of 1 to 10 as being relevant or non-relevant. Since there are 10 different elements in your first page, there are 2 to the 10 different ways in which you can do this. So you could possibly label the first document as relevant and everyone else as non-relevant, or you could decide that first, second are relevant, the rest are non-relevant, and so on. So that gives you 2 to the 10. And once this information goes back to the search engine, it re-ranks every document using any one particular algorithm, so that every document between 11 onwards gets its position changed. Hopefully all the relevant ones come up on top and the irrelevant ones go below. That's what you'd hope for. So what we are saying is that instead of just showing real users one of these screens for any given query and asking them to pass a judgment, because that judgment is going to be unique only to that user for that point in time. So our aim is that we'll just measure what would happen if they did each one of these 210 different evaluations. And it's our belief that if you did that, you're sort of getting a more holistic view of what's happening with the algorithm, because you've evaluated every possible user action. So I've just given 2 branches in the tree, the first and the last. So if the first combination could possibly be one as relevant and all the others as non-relevant, then what would happen? I mentioned we're talking about target document search. So you're searching for a single document. This single document existed at rank R initial in the original list. And post feedback, it's got re-ranked. And if it was combination 1, then say it reached rank R1, right? So the difference in R initial and R1 gives you what the feedback algorithm itself has done. Hopefully R initial minus R1 will be negative. So that would mean that the target has gone up, right? So to run our experiments, we used a set of queries that MSN had collected. So these were query result pairs, exactly what we wanted. So there was a query and a given URL which was deemed relevant to this specific query. What we did was took this query, used the MSN API, and collected 500 results. For a large proportion of the queries, we found that the results, the target URL was in the top 10. And if it is, then there's no point using feedback because it's already there in the first page. And what you're trying to measure is, if it's beyond page 1, then how quickly can you bring it up? So we used the remaining queries, which is about 54. So each of the documents, when we are using our algorithms, need to be represented in a certain way. And to represent them, you need words, as you would expect. From where you get these words gives you 3 different ways to represent your documents. The first one we used is the actual text on the page itself. This is standard what would happen if you did search on the web. You're looking for your query to exist in actual text of the page itself. We're also used to search engines returning snippets in the search result page. And this is slightly more targeted in the sense that out of the entire text of the page, you've already identified the bits that are going to be relevant to the query. The third is the anchor text. So if you have a page linking into this page, then what do they use when they're just over the hyperlink? And the heuristic is, of course, that people take care when they punch in the anchor text. And it's very likely that the words that you see on the anchor text are going to be more helpful than the actual text of the page. So as I mentioned, we are doing a brute force strategy of evaluating every possible user action. So if you have I can be anything between 1 and 1024. And the best improvement for a given query is the best difference that is the biggest difference that you can get for R initial minus Ri. So in the initial retrieval, the target document existed at R initial. You can plot the best improvement for that given tree versus the initial rank. Just to give you the logic behind saying why we compare it to rank y equals x minus 11, you can imagine a document that existed at rank 50 after the initial query. You gave it some judgments and you're expecting it to get bubbled up. How high can it go? It can only go to the first position on page 2, which is rank 11. So this sort of gives you a ceiling. Your feedback algorithm can't do better than this. What you're trying to measure is how close to this line does your feedback algorithm do. Yeah, again, you can do average improvement rather than best improvement. We're interested in the upper limit. So that's what happened when we used Rcio. And those are the 3 representations that I talked about. The dotted line is the y equals x minus 11. And the solid line is the best fit line for those set of points. Each point on those plots is a query. So we had 54 queries, so you should find 54 dots on each of those graphs. For me, it was expected, but you do find that for the full text, the solid line does not quite match up to the upper limit. It gets slightly better for snippets. And for anchor text, you do manage to touch the best case scenario. So in terms of the evidence provided to you by words, anchor text is much better than either full text or snippets, essentially suggesting that if you really want to use relevance feedback, then use terms from anchor text rather than content of the page. Probably expected. Sorry. Just randomly, I passed the HTML for the words and just 1,000. There's no reason except that just for computational aspects. But apart from that, yeah, I mentioned we're doing all this to compare feedback algorithms, so you can do the same thing with the second algorithm, which is the Robertson Spark Jones algorithm, and we found that it really didn't do as well. Well, the trend is the same in the sense that full text is bad, snippets is slightly better, anchor text is the best, but it doesn't get as close to the upper limit as Rcio did. My personal view is that this algorithm is quite sensitive to the feedback that's given. So there's very high variance in what happens across different branches in the tree. And I also saw that the variance in performance across the 3 different representations is highest for this particular algorithm. So in Rcio, it did fairly well for the first 2 representations, and it did well on the last one. But this one, the performance varies widely across the representations. The third algorithm is probably the best overall. And in fact, in the case of anchor text, it's just practically on the upper limit. This is what you'd like to see. Plus, it's less sensitive to the representation itself, which means for some reason you can't get the anchor text. You could still go ahead and use full text. You'll do okay. So if you don't like pictures, then yeah. Sorry.
Have you considered for, say, the average user that uses the search engine to look for a particular target, that they may not look past, say, the 5th result, in which case the relevance feedback may outperform, say, y equals x minus 6 or something like that.
Yeah. Essentially, I'm selling the methodology more than I'm selling the results of the comparison. So if you believe that top 5 is better, then all you have to do is just go and change it to, instead of 1024, you do 32. Yeah, we're selling the methodology as much as we're selling the results. The results themselves are, people have evaluated each of these feedback algorithms in much more detail than I have. For example, they all have parameters, and I didn't exactly sit down and tune them. So maybe if I did, Robertson Spark Jones will suddenly come up and beat the others. So essentially, it's the fact that we think that this is how you should be evaluating them rather than sitting down. So that kind of thing. And there's also sort of background to this in the sense that before we did web search, we had evaluated these algorithms in a different context, the context of searching on small display devices, and that's where this sort of brute force searching methodology came from. But yeah, just the take home should be that maybe if you have enough machine power, then maybe this is how you should be evaluating. Right. So just getting back to the results. So in terms of words, for Rcio, I think anchor text did best. Full text was slightly noisy. It possibly didn't give you a very good idea of the content of the page. RSJ, again, even though anchor text got pretty good, it's still not great. The Bayesian one did well overall, did best overall, and it was again stable across representations.
Since you here mentioning the methods, I was just curious about the cost of performing Bayesian-based relevance feedback compared to others.
It's definitely the most expensive, mainly because of query, right? So we all know that queries in text tend to be quite short, and once you modified the query, the only documents that you need to re-rank are documents that contain at least one of the words. Right, so in that sense, even if you have a million documents, if you have a 3-word query, you're probably going to have to re-rank an extremely small fraction of those. For the Bayesian one, you use similarity between documents. So that comparison is a lot bigger than comparing a query to a document. So yes, Bayesian is definitely the most expensive lot. And it also has to re-rank every document in the collection rather than in the previous case where you only re-rank the documents that contain at least one query term.
However, it does work well on anchor text.
Yeah,
which is
yeah.
A smaller, I would expect computation or short document may not be feedback.
Yeah, in the sense that all pages linking into Microsoft will probably only use Microsoft. They might use some other words, but yeah, the set won't be too big. So each document itself, the number of features will be very small. Right, so we were considering best improvement, but it could just be that this best improvement was caused by this really vague combination. I mean, something like, pick document 2379 as being relevant. and it's very unlikely that a real user would actually use that combination. And if they didn't, then it's very unlikely that you're going to get this best improvement. So we're still sort of back to square one. We don't know how well any given user might do. So what we now have to try and estimate is, if a monkey came down and sat down in front of your search engine and gave you this feedback, what's likely to happen, right? An algorithm that's going to still end up providing benefit, even in that sort of an extreme case, is probably the one that you want to use, because you want to kind of limit your damages as much as possible. So what we define there is P change, which is R initial minus Ri divided by 10, which is essentially the number of pages that are going to be reduced if it is positive. And so in negative, it means that your feedback has caused trouble. So what you're trying to do now is just putting it in buckets in terms of how many pages lesser are you going to be viewing if you did give the feedback. And you, for I ranging from 1 to 1024, for a given query, what are the different changes in pages that you saw? What just means is that if your feedback just causes change in 1 rank or 2 ranks, then it doesn't matter that much, because it will still be on the same page. So in terms of standard web search interfaces, that doesn't mean much. Whereas if it moved from rank 45 to 36, then that's a change of 1 page, and you'd like that. Whereas if it moved from 45 to 56, then that's a negative, and you don't want that, right? And you just calculate all the P changes that you can get over all the I's, and you plot the cumulative distribution of that. So you just add for increasing buckets. This is what you get. So for Rcio, on the x-axis is the number of pages that change. And you'll find that a large proportion of them are negative, which means that there were so many combinations of feedback that caused trouble. They didn't benefit the user in any way. And there's also a large proportion that you bettered the ranking in terms of pushing the target up. I've drawn a sort of vertical line at 0, which is the probability that nothing will happen. So you might go through the trouble of providing the feedback, but nothing happens, in the sense that this result continues to stay on the same page. And that gives you the probability of how many of the 1024 options is going to benefit the user. So everything to the right of the vertical line is going to benefit the user. So if you see where the vertical line intersects each of those curves, then that's exactly that probability. And it's roughly around 0.7, I think, for Rcio, and it's about 0.75 for RSJ, and about 0.445, something like that, for Bayesian. So what this means is that 60% of the cases for the Bayesian one is going to cause a reduction in performance, and about 70% of the cases for Rcio is going to cause 70% is going to cause in case of Rcio. So again, we see that the Bayesian one seems to be better. So going back to our monkey analogy, if the monkey comes along and just randomly labels them as being relevant, then still in about 60% of the cases, you're going to get the target to move up in the case of the Bayesian algorithm. Which is not that surprising, because you shouldn't think that any of these numbers are too high, because the initial set of results came from a reputed search engine, so they're all relevant to some extent. So the numbers are not that high. Yeah, so we've just used a feedback evaluation methodology to show that you could potentially get decent benefits of using feedback. And we've, so as I mentioned, we just showed the framework of how to do it, and we've performed one comparison just to concretize the example, and compared these 3 algorithms and have a suggestion for which one which one you should probably use. And some of the stuff that I just spoke about was published in a paper at the World Wide Web conference in 05. Right, so now on to the second aspect of my talk.
Perhaps any questions for the first part?
Are you guys considering going on to analyze categorical search?
Probably not, because it's very difficult. I mean, even if I perform brute force, the thing is that the brute force is only possible if it is computationally feasible. So if I have a target document, I know kind of exactly what to measure. For categories, suddenly it becomes very much larger sort of options for the termination condition, in the sense that what is the end of the search. And so if I can't signify what is the end of the search, I can't say when I have to measure. And if I continue doing brute force, it sort of explodes, and it's just not computationally tractable, essentially. But I do believe that there is some sort of correlation between target and concept search. So in some sense, it's very, very likely that evaluating it in terms of target will give you an indication of what will happen if you do it in concept.
Okay, maybe we can continue now with the second part.
Yeah. So this is a very practical problem, which I mean, obviously, because most companies work behind closed doors, we don't know whether it's being done already in the industry, but it definitely is a very active research topic, which is estimating how well you did on a query. So what this means is that you're a search engine, you've got a query, you've used your favorite retrieval algorithm, and you retrieved a set. Can you tell me how well you did on this query? How likely is it that the user is going to find what they're looking for? It's very important to be able to say this, because for a variety of reasons, all of which I'll just outline in a second. So yeah, I don't have to sell search in Microsoft, I'm guessing, but it's how all of us find information on the web right now. And at least in the academic community, how evaluation is performed is that there's the set of queries over which we'd like to perform well on average. So there are two systems. The average of one is better than the average of the other. But that doesn't say much really, because there might be some queries which are performing really badly, even on the system that had high average performance. The thing to remember is that users tend to remember bad mistakes. So I go to a search engine and it returns me a set of non-relevant results. I'm likely to remember that, and as a search engine, it's important for them to make sure that doesn't happen in some form, just letting the user know, or something of that sort. And as I mentioned on the slide there, being able to take this sort of action relies on you knowing that you've done badly. So how do you say now that you've done badly? So these are I put down 4, there are probably many, many more. So first is what I mentioned, providing feedback to the user. So instead of just giving them pages of irrelevant results, maybe you just put up a dialogue there that says, look, I didn't understand what you told me. Can you refine your query? And then I'll probably help you better. The second is coming from the other side, so not the user, but the person controlling the collection that's being searched. So maybe the guy's crawling for the search engine. They repeatedly find that there's this particular set of queries on which the engine is performing very badly. Maybe it's because they haven't crawled the data that addresses that query. So now they know that they need to obtain this extra data from somewhere. The third is another interesting problem about which is in relation to meta search. So in meta search, what happens is that different engines return their results, and I'm sitting in the middle, and I combine them and return it to the user. The idea being that combining them is going to be better than any individual one. But at the present moment, the combining is done very simplistically. You just take all the lists, put them together, count how many times any given result occurs across the different engines, and that's used to alter the ranking when it's combined. But if you knew how well each engine did, then that gives you a sort of confidence in each of these engines, and you can relatively weight the results of each engine when you combine. And I mean, it's quite logical that that sort of combination will probably be better than this dumb combination in a sense. The last one is also important. I mean, most of these search engines have spent so much time developing retrieval functions that they probably have a host of different retrieval functions, some of which are probably going to be more complicated than the other. Complicated also in the sense of being computationally harder. So you want to be able to return results to the user very quickly. That restricts the different retrieval functions you can use. All the complicated ones, you have to be put to the side because they're just too slow. But at the same time, you want to prevent user dissatisfaction. So if you realize that using the simpler retrieval function I haven't done well, then go to the harder one. Hopefully the harder one, by harder I mean the one that is more computationally costly, will give you better results. Right, so when I say I want to predict how well I did on a query, there are different ways in which I can pass this judgment about the query's performance. I can take a single query A and say that it was good or it was bad. Or I can make a comparison between two queries and say that the performance on query A was better than performance on query B. Obviously the first one is what would be useful in a real world scenario, because you just get one query and you should be able to say what you did on that. But in a sort of a simpler problem is the relative judgment, and that's what we'll be concentrating on. So I'm going to give you 4 or 5 different queries, and you should be able to tell me what's the relative performance of your favorite retrieval algorithm on each of those queries. So we need to also mention what performance is. So what performance of a query are you trying to predict? There are a lot of different things, of course. I mean, as old as the field of text retrieval is, there are metrics to qualify what performance is. And we'll concentrate on precision. So what you're trying to do is get as many relevant documents as possible and get them as high in the ranking as possible. And how you calculate precision is given there, a fairly standard metric in the field. Right, so this is the framework in which we are going to be working. So you give me a set of queries Q and a collection C, which is the collection is what's going to be searched on, and the set of queries gives me each individual query. I take the query, I issue it against the collection, and I collect the set of results that were returned to me by the search engine, say the set capital DI. And now I have relevance judgments provided to me for that given query. I use that to judge DI, and then it gives me a measure of how well I did on this given query. This is the goal judgment, right? So you can calculate the average precision, say, for each query in your set Q, and then arrange them in terms of the average precision, possibly placing the query with highest average precision at the top and the worst one at the bottom. What you're now trying to do is predict that ranking. Use whatever method you have to try and repeat that ranking again to account for the scenario when you didn't have the relevance judgments. So now, without this relevance judgments, what sort of aspects of the retrieval process can you use to try and reproduce that ranking? And this, in the academic community at least, was interesting because it was part of what's called the robust track in the text retrieval conference. Don't know if I should go into much detail on the slide. It's possibly only of academic interest. Just to give you a quick clue of what people have tried in the past, they've used something like query length. They think that shorter queries you're going to perform badly. They use something like the score of the top ranking document. If the top ranking document had a high score, then maybe you did well. Then they use things like standard deviation of the top ranking documents. Again, you'd like not only the first document but the whole set of top few documents to rank high, etc. They've tried a variety of different things, and the reason we are continuing to look at this problem is that they have not been very successful. This is the hypothesis that we work on. What documents for us are points in a very high dimensional term space. Again, a query is a pseudo document in that space. You use nearest neighbor with some similarity metric to give you the retrieved set. And what we are trying to say is that if this retrieved set is random in some sense, then you've done badly, and you're trying to measure the structure in this retrieved set. The existence of the structure is going to be useful to you, because you're going to say that if such a structure exists, then you predict that you've done well. And for measuring this existence of structure, we use 4 different features. What clustering tendency is a term that's existed in the literature for a while now. There's document perturbation. I'll explain what each of these are in a second. Third one is local intrinsic dimensionality, and the fourth one is query perturbation. They were all designed to sort of try and measure some statistical regularity within the points that correspond to the retrieved set. The logic behind each of them I'll explain as we go along. There's what's called the cluster hypothesis in information retrieval, which essentially states that documents that are relevant to a given query are going to be similar to each other. So we think that an extension of this is that if there's clusterability in the retrieved set, then you've done well. Now what you need to do is measure this clusterability. One way of doing it is actually taking your favorite clustering algorithm and actually clustering the retrieved set. And if it does form nice, well-separated clusters, then you can say, okay, I think the data set is clusterable. But this would involve actually selecting a clustering function in the first place and then applying it on this data set. So we want to try and get around having to actually cluster the thing. So an a priori analysis, in the sense that without having to cluster itself beforehand, you're trying to say how well any clustering algorithm would potentially work on this data set. Sort of pictorial view of what we are trying to do. The statistic we use for measuring the clustering tendency is what's called the Cox-Lewis statistic. It's about 35 years old, and it works as follows. I've shown 2 different data sets. The one on the left is a set of 100 points sampled from 2 Gaussians. So you have one nice cluster there and one nice cluster there. And there's this other data set that's fairly random. You want to be able to cluster points like the sets on your left. You don't want to be pushing the data set on your right through a clustering algorithm, because it's going to give you nonsense. And what is it about the data set on the left that makes it more clusterable than the one on the right? To measure exactly that, you start off with what's called the sampling window, essentially a boundary that contains all the points. Within this boundary, you randomly pick what's called a sampling origin. You use the similarity metric you're using to find the nearest neighbor for the sampling origin and call it the mark point. Then you find the nearest neighbor of the mark point. So you have 2 distances now, the distance between the sampling origin and the mark point given by dRand, and the distance between the mark point and its nearest neighbor called dNN. What would happen if you took a ratio of those 2 distances? On your left, that ratio is going to be quite high, whereas on the right, the ratio is going to be quite less. So you can imagine if I repeatedly sampled for the origin all over the sampling window, it would give me a reliable estimate of that ratio, and then I'll use that to compare 2 different data sets and say one is more clusterable than the other. So that was the first feature. The second one is what we call document perturbation. The logic is essentially this. If you have a set of documents, D, pick one document in that DI and issue it as a query against D. What would you expect to see? You'd really ideally want to see that document DI is ranked first again, unless there's been some mistake in your retrieval algorithm. What we do now is perturb DI in some sense. So make it a noisy query and then issue it against the collection again and measure what happens with this addition of noise. You'd expect that if you add increasing amounts of noise, DI will stop being ranked first with respect to itself. This rank will continually fall, and you want to be able to measure the effect of the amount of noise you add to how quickly this ranking falls off. And this is how we add the noise. It's nothing fancy. You just pick a random number and add it to the term weight and change it by a certain amount. What's important to note is that the alpha value over there controls how much you change it by. So the larger the alpha, the larger you change it. When alpha is really small, then the added noise does not cause any change. Whereas if alpha is quite high, then you get essentially random behavior. So we do this perturbation analysis on every document in the retrieve set, essentially trying to see how quickly this ranking changes. And we just say that if the ranking changes fast, then you have a random set of points. Please remember that we are saying that random points means that your retrieve set is bad. And we measure this change by plotting a curve and calculating the slope. And the bottom line just tells you that if it changes slowly, then you've done better because your result set is less random. The third feature we use is what's called the local intrinsic dimensionality. I don't know if I should go into too much detail, but essentially, again, this is a measure of how random your data set is. What we're trying to do is there are techniques known as there's a technique known as latent semantic indexing, which essentially says that points lie on a lower dimensional subspace, and what is the optimal number of axes you have to use on your subspace when you perform LSI. You try and measure that. The lower it is, the more random the set of points, because random points have low intrinsic dimensionality. So just gives you details of how we calculate this. Essentially, we take every point in the retrieve set, look at its neighborhood, and for each neighborhood we calculate the intrinsic dimensionality. And as you increase the size of the neighborhood, the intrinsic dimensionality should hopefully increase. And how quickly it increases is an indication of the randomness in that neighborhood. The last feature is what's called query perturbation. So what you did when you have an initial query is just drop a point in the midst of all the documents, and then you found that its closest neighbors. What would happen if the query was perturbed a little bit and fell a slightly different neighborhood? You retrieve a different set of results. So how does the perturbation you introduced affect the retrieve set of results? If the query is stable in some sense, then regardless of how much noise you add, you should still get the same set of results. And that's how we perturb the query. Just again, pick a sample from a Gaussian and just add the noise there. Again, alpha controls the amount of noise that you're adding. And so after perturbation, you're collecting a new data set D dash, and now you need to measure the overlap between D and D dash. And we do that by using what's called the Levenstein distance, which is essentially a measure of how many insertions, deletions, and modifications you need to turn one ranking into another. And again, we plot a curve that measures the dependence between this Levenstein distance and alpha. And you're again saying that if a query is stable, then it's unlikely that adding any kind of noise is going to alter the data set retrieved. So this is experimental results. That's the standard information retrieval data set. The given set of given set of topics that we used. We used the standard TF-IDF representation. We collected 100 results. We used the relevance judgments given to us to calculate actual achieved performance. And now, as I mentioned, we're trying to predict that. We predict that using each of our features. And now we need to compare how the two rankings to guess how good our prediction was. To make that comparison between the two rankings, we use the Kendall tau metric, which is standard for comparing two different rankings. And we see the performance of each of our features. The two best performing ones are the clustering tendency and the document perturbation. And individually, they perform better than the best reported result before us on this data set. As you would expect, if you have different features, then you try and combine them. We tried and combined them too. And instead of having some sort of complicated way of combining them, we just wanted to do simple arithmetic means. But before we did that, since each measure was in a different numerical range, we needed to normalize them in a certain way so that they all become comparable numerically. And we tried out 3 different ways of normalizing them. And since we have 4 measures, it's not just combining all 4. You can combine them in different ways, either 3 of them or 2 of them, which 3 of them. And so we tried out all possible subsets. That's the results. The Kendall tau got pushed up a little bit more to 0.562 for the best predictor, which was using 3 of our features with one particular type of normalization. And the other normalizations, they all do pretty well. So just to give you an example of where and how you'd use this, I mentioned at the start that you want to be able to identify the bad queries. So what we did was take the same queries that we had and arrange them in terms of their average precision, such that the worst ones were at the bottom. So these are the queries that your engine couldn't handle. It just couldn't give out the relevant documents. Then you collect the bottom few, in 20s in this case. So you take the bottom 20 in the actual ranking. You take the bottom 20 in your predicted ranking. How common are they? What sort of overlap do you have? Because your prediction said that these are the 20 worst that you did on, and your actual ones, well, they were the actual worst ones. How well were you able to identify these? I think it did fairly okay. We did for 10% lowest query, so which means the bottom 20, we got 55% of them right. And as you would imagine, when we start going up, I think you're being more and more lenient. We got it more or less right. So that's just a quick conclusion slide, just illustrating that it's not just a bunch of people in universities thinking up stuff that might not be useful. I think it's a very valid problem for most search engines in being able to predict before actually performing, before returning results to the user, how well they've done on this given query. And our features are fairly efficient because they only work on a small subset, the set that you got as the retrieve set. And just as an aside, this is almost exactly the same presentation I made at SIGIR yesterday, where this paper has been accepted for publication. And that's it.
Okay. Any questions? Okay, well, thank you very much.